Hello, everyone, and welcome to the next session at the Best Annual Institute. I'm Jamie Page. I'm a program manager at Lawrence Berkeley National Lab, and I'd like to introduce our next speaker. This is Woody Delp. Woody has been at the lab since 1995 and has worked in a variety of project areas related to HVAC systems and how these systems actually operate in real buildings. His work has ranged from measuring duct leakage in light commercial buildings to understanding how pollutants move in large buildings. And he is equally at home with everything from residential HVAC systems to the systems found in the largest buildings. He has a PhD in mechanical engineering from the University of Missouri in Rolla, and his graduate work involved modeling how much ventilation comes into variable air volume systems as they operate across a wide range of climates and seasons. He grew up in the Rolla area and worked in a family-owned HVAC business. So he comes at this from a very young age and is well-versed in designing and installing complex systems for a variety of places. I might also note that he was the winner of a director's award for last year for some of his work in this area. And he will be covering a different topic, looking at buildings and wildfires. So without further ado, let me hand the meeting over to Woody.
Okay, thank you. And yeah, I may come to it from a very young age, but I am no longer at that very young age. But we will, we get by. So what I'm going to talk about today is buildings and wildfires. Buildings and wildfires, and we talk about the wildfires, that means smoke. Smoke means particulate matter and something we specifically call PM 2.5. 2.5 micron and smaller. And relatively recently, within the last 5 years, have been some devices that are coming on the market that are supposed to offer, numbers that should be pretty good, but how in the world can they do that if the sensor that they're relying on generally only costs about 20 bucks buying them, on an OEM scale? The real tools that I'll call here that the air quality management districts use, my research tools that we've had in our bag of tricks for a while, cost many thousands of dollars. And if these things are any good, how can we use them? What kind of pitfalls do we need to be aware of? So I'm going to go over, just sort of a little bit of a primer on PM, particulate matter 101. It's a little bit of a primer on particle detection, because understanding how these instruments actually work is kind of important whenever you're dealing with the data that come off of them. And we're obviously, according to the title of the talk, going to talk about some wildfires. And then I'm going to focus a little bit on probably the most popular, the most common sensor that people are aware of, the purple air device. And then how we've used some of the purple airs on the LBNL campus to understand how our buildings were performing during some of the recent smoke events. So let's start off with the primer here for the PM 101. This is a very common figure that anytime you start talking about PM, people use this figure from the EPA. And human hairs, from a particle science point of view, an indoor particle science point of view, are boulders in size. I mean, they're ginormous. They're in this 50 to 70 micrometer size range. Beach sand that blows around and gets in your food whenever you're at the beach is even bigger in the 90 micrometers. Some of the respiratory fluids that we sneeze, that people were scared about people coughing out now, may be in some of these large sizes. The PM2.5 is 2.5 microns or smaller, and they're trying to show you here in this little graphic that these are these little red things that are 2.5 micron. And they are made up of, this is sort of also showing the sizes of different things that could possibly be airborne. But we're going to focus on the combustion products. And direct products of combustion are usually these really small things, down in the 10 to 60, 80 nanometers or so. But whenever we have a wildfire fire, you've got a lot of energetic burning, there's incomplete combustion that kicks it up in this giant plume. There's a lot of stuff that happens after that initial burn. These particles agglomerate and they sort of like clump together, different things condense on them, and it ends up, by the time it reaches the Bay Area or some miles, could be, you know, even a continental scale away, these things grow in size and are in this, you know, 0.2, 0.3 micron, which people also call the accumulation mode. That's important because that's kind of hard to get rid of. Below a certain size, things tend to stick to surfaces. Above a certain size, they're easy to filter. And in this range, it happens to be the unfortunate one where they sneak through filters. They don't necessarily stick to things all that carefully, but we can also sort of see them in here. If they were strictly down in the smaller size, we would have some problems sensing them or seeing them. And there's an analogous sort of thing going on now that everybody's aware of with the pandemic. Viruses tend to be down in this size, but they're never by themselves. We always find them in like little spitballs. And so they're going to be in the, you know, a few in stuff that's more in the few micron size up to, you know, tens or even hundreds of microns in size. Now, staying on with the PM primer here, there's standards for outdoors, and there's standards for the industrial environment. The actual numbers that we try to keep things below from the standards point of view is we want things in the, you know, 10 to 12 micrograms per cubic meter. We start to get a little bit, you know, above, you know, the 30 to 40, that's starting to put us into, you know, kind of a worrying zone. But if we look at the occupational exposure numbers that are allowed, well, these are, you know, a factor of 1,000 higher. So we're certainly paying more attention to the outdoor long-term chronic exposure, and we can just assume that this is the types of numbers which we should be applying also on indoors. There have been some efforts to try to get indoor numbers, but we're generally happy if the numbers are 10 micrograms per cubic meter or lower, and we start to get unhappy if they're, you know, north of this 30, 35. Most people are more familiar, instead of these raw unit numbers, they're more familiar with, because it's reported in the news, the AQI, the air quality index. And the point of the air quality index is to try to give, you know, a more meaningful scale using different pollutants besides just PM2.5. You know, there's ozone in here, there's some other pollutants that are put in that will map out to the same AQI score, you know, green, yellow, orange, red, purple, and then just like you're really certainly unhealthy. And with the recent wildfires, we were spending time in this purple to unhealthy category. Now, one thing to point out is these numbers are based on a 24-hour average. And if the conditions are changing, they allow you to compute this based on 3-hour averages. And another thing, there's going to be lags and steps in these reported values. As the numbers, you know, go up, obviously, if it's based on an average, that's going to change the way the reporting values are coming out. So we really never were looking at particle levels outdoors or indoors, and the indoors is also providing a time lag to it. We need to do some averaging to the numbers. Now, what we've used, you know, in the past, so we have the federal, you know, reference method, federal equivalent methods, and this particular instrument here runs about $30,000. That's what's setting down off of, you know, off of University Avenue, just off of the edge of I-80, there between the roadway and that place where people will water ski. And it's $30,000. It provides numbers once an hour, and it's sort of gives us the right number. And what we have used in the past here at LBL, as well as some other researchers and industrial hygiene groups, these research grade instruments tend to cost in the ballpark of, you know, $5,000 to $10,000. And recently, these consumer-based devices are coming onto the market that you can buy for, generally under $300, and it comes with, depending on the product, various levels of user interfaces that are, web-based or iPhone-based, and you can do quite a bit with the numbers coming off of them, all with a sensor that is in the ballpark of $20. I think some of them are even getting cheaper than that now. Now the research grade instruments, as well as the current consumer grade instruments, all use an optical sensing method. And what they tend to do is induce the particles, a flow of air through a small chamber, and they shine generally a laser light on that, and they look at the scattered light that comes off of that. And the mass is generally proportional to the amount of light that's, to the scattering intensity. However, and this is where, flashing lights, bells, whistles, sirens, everybody needs to be aware of this, is that this response is a function of the density of the particles, the particle sizes. So if it's a wildfire smoke, it's going to have one particle size. If it's something, driving down this trail here, it's going to kick up the stuff that's coarser. If it's driving down the trail, it's going to be crustal material. It's going to be dust, dirt from the soil, and that's going to have different optical properties than semi-volatiles that are in the wildfire smoke. And on our research grade instruments, they say source specific calibrations are required. And so you can have the same amount of mass in the air, depending on what the original source of that material was, it will cause the instrument to ring a different number. And that turns out to be quite a challenge for us. And here, this is showing sort of cross-sectional areas of two of our research grade instruments, and they're precision machine bodies. Everything's very precisely aligned. You've got controlled pumps that control the flow very carefully through here. And this one shows how also you get what's called a sheath airflow that tries to strip off some of the particles and provide very clean air around this chamber, which has all the optics and the measurement path in it, so it can stay relatively clean over time. Needless to say, these $15, $20 sensors are taking some shortcuts, and they generally don't have the controlled pumps. They don't have the precisely machined internal bodies on these things. So are they doing any good? So let's take a look at some of our wildfire data, which is why we're here today. And this picture has gotten quite a bit of attention, and we love the picture. I mean, well, it was pretty bad at the time, but this is from the campfire that struck in November of 2018. And we see on the one side, these are pictures taken at the lab, just a couple of weeks apart, with and without the fire, obviously. And down here, underneath this arrow, is pointing roughly where the reference monitor, that reports for the Berkeley, area, what our quote true numbers are. And we see in these little inset plots there were some purple air devices that were distributed in the vicinity of this reference monitor. And this is showing what kind of response we had. So whenever the air was clean, remember I said 10 micrograms per cubic meter is very good levels. So we see that we were getting, it was responding with the correct numbers whenever the air was clean. That really doesn't matter if it's clean. We don't need to understand what the air is anyway. But then we had high numbers. Now my scale has changed here. We're getting up into alarmingly high numbers. These are truly, the air is bad outside. You don't really need a sensor to tell you that if it looks like this anyway. But the important thing here is whenever the air was at 150, this sensor tended to think that it was closer to 300. And so let's look at some instruments that we had inside a laboratory space that we could open, and make it look like outdoors by opening some doors and turning on a fan. And so we were able to come up with some calibration factors for a series of what I'm calling our consumer grade devices, as well as a couple of our research instruments. And for the most part, things are correlated quite well. And I've changed the scales a little bit here, where I'm looking at the reported value, in this case of a purple air, and then versus what my true reference value was inside the room. And for the most part, we're seeing that things were over-reporting by about a factor of 2. Another interesting thing here is the purple air, and this one was an air quality egg. We're using the same sensors inside, and we were getting roughly the same results. However, we did have a bad egg in the group because one of the sensors was throwing out some erroneous numbers, but the way they've got 2 sensors twinned inside, and they were averaging these 2 numbers together, and only one of the 2 sensors was throwing an erroneous number. So it was yielding results that looked possible, but whenever you compare it to the truth, was not exactly right. And even our, one of the expensive instruments, we can see and hear that there's also some trends that were occurring where we were getting different qualities of smoke over the course of this roughly 2-week period that we had the smoke impacting the Bay Area. There were some periods where we had a different calibration that would apply for that particular point in time when the smoke was coming in, and at other times we had different calibrations, which explains some of the differences that we're seeing across this. It's not a perfect correlations, but they are pretty good. So what we learned about that is all the optical devices, both the low cost and the research grades, over-report on the wildfire smoke. They over-report by about a factor of 2. And that was pretty common among that. And so from this, I want to be able to say is like, know your data. Like I say this to people all the time. With the case of our PM data, you can pretty much count it's usually wrong, but it's oftentimes correctable. And by that, there's we had a paper resulting from looking at some of the wildfire smoke as well as a group at EPA. And we're both providing ways to correct some of the sensors that are out there. And the EPA one in particular has been utilized by Purple Air on their, on their recent map. They made some updates to that. And this is probably what most people here are familiar with right now, because this has gotten a lot of airplay whenever we have the smoke in the Bay Area and elsewhere. And so if we can take a look at one of these maps, so this is the map zoomed in on Berkeley, we see a couple of different things here I'd like to point out. There's circles that show, and what they're showing right now is the AQI number based on PM2.5. You can drop this menu down and have it change to, the actual concentrations. You can have it show several different things that the sensor is actually reporting out at the time. And it happens to be set, excuse me, the US EPA correction factor, which is that one paper I was pointing out. And so these are supposedly corrected values according to that one paper and reporting the AQI index score at the time. Now, the other thing to point out on the map is some of these dots have a dark circle around them. And that dark circle indicates an indoor placed sensor. And so you can start to glance at these, and if you zoom in, you can see an indoor-outdoor pair and hopefully get an idea on what the indoor-outdoor ratio is. And now on the Purple Air is using a sensor from a company called Plantower, and Purple Air uses this data as reported by the sensor just as is. Some other companies are applying dynamic corrections and do it sort of in the cloud, but Purple Air is using the raw sensor data and spitting it out. And in the header of the file, there's 2 different things that show PM2.5. The one is quote, according to the manual, intended for indoor readings, and this one that's underscore ATM is intended for outdoor readings. Now, I happened to run into somebody at a conference, and this sensor was developed in China, and it was calibrated by placing a van close to the US Embassy and taking their reference instruments, much like it's the same instrument that we have down off of University Avenue, and seeing what the results are. And remember how I said that whenever you get a different source, it can cause the instrument to ring differently. They found that whenever there was bad air in Beijing, they had to apply an adjustment to get things to match. And so the header that's called CF1, is what I'm calling the truly uncorrected data, and the CF-ATM is a correction that applied to Beijing air at the time that they were doing the calibration work for their instrument. And when calculating an indoor-outdoor ratio, which is important for understanding how your building's working, if we start to mix these things up, we're not comparing apples to apples here. So we want to be able to use the CF1. And unfortunately, the purple air map is mixing them up. Whenever it's reporting a value that's indoor, it's using the CF1. And whenever it's reporting a value that's outdoor, it's using this correction factor ATM. So I've said it a couple times, we want to know how well our buildings are performing. For the wildfire smoke, smog, anything else that's coming from outdoors, the principal metric that we like to work with is called the indoor-outdoor ratio. And again, we want to make sure it's an apples-to-apples comparison. So the best way to do that is to use the same sensors, same devices. In the research world, one thing which a lot of people have done is they will even use physically the same instrument and have a tube that switches on a manifold going from inside to outside to inside to outside. And that's probably the best way to do it. But if we're using the same, the same devices, recording the same channels, we can still get, pretty darn robust and solid numbers. Now let's look at the LBL campus. Nice little overview of the LBL campus from the website, their little 3D type of false 3D map. And looking at the, a more general type of map for the campus, we see that we have a lot of purple air sensors scattered throughout the campus now. And in addition to this, all the buildings here there's a purple air outdoor only on top of a weather tower that's on the campus. There's also a purple air monitor in the outside air intake on this building, which is the new high performance computing building. And there's a purple air monitor at the outdoor intake on the roof of building 67, which is a mixed use building. And a few months ago now, it's hard to tell time in this age of COVID, but we were approached by facilities and they were looking at the purple air map and they said something's going wrong because building 67 looks like, they knew that it was not, the highest quality building from the amount of filtration they had in it, but it was consistently looking like the air was worse inside than outside. And remember, this is the outside monitor and this is the quote, the inside monitor, and it looked like, they were running about even, but a lot of the times it was worse inside than outside. And well, that was just an artifact because we're not comparing apples to apples here. We're having apples to oranges comparison. So if we bring in the proper monitors, this is what it really was looking like on the roof, in comparison to what was inside. So we were getting numbers that were, 400 here, they were like 250 here. So we were getting something that was like, a 40% reduction or so. It wasn't worse inside than outside. Now, if we continue that, and again, remember I said that there's fluctuations outside. Actually, back up a second here. This is 5-minute average data. On outdoor data in particular, you can see fluctuations that happen relatively rapidly. Indoors, once it comes inside, we've got the time constants of, what's the air change rate in your building, what's your VFD running at. And so things are going to be much more uniform and sort of like behave in a slower manner. But we certainly, that we're doing these comparisons, we need to do some form of averaging. Now I'm skipping all the steps that it takes to get the raw data, average it, and present it. And so there are quite a few steps involved, but this is showing that same building that I just was showing they thought was a problematic building. As it turned out, over this period of time, this happens to be, I think the 10th was the day in September where we had the really strange apocalyptic orange sky. And then the marine layer broke and the pollutants dropped down, and we had really horrific outdoor air quality. And throughout that, this building 67 was providing us, around a 40% reduction of outside, but 40% of a high number was still a high number. These are uncorrected. So if we correct those by just our general, we know that they were over-reporting by about a factor of 2. That still puts us on both outside and inside in pretty high numbers. If we look at the high performance computing center on the campus, this thing has, I think, MERV 16 filters, and we were getting an 85–90% reduction in the outdoor values over that period of time. Now, if we go to building 90, which some of us here have more experience with than others, it's everybody's favorite building to hate there at the LBL campus. And we're seeing that it has it has MERV 13 filters in there now. The system shuts down at night. And while the system's running, we were getting pretty decent performance of the building. Whenever they shut the system off at night, things creep back up relatively quickly. And then in the morning, if you turn the system on, it plunges back down. And I'm not showing it here, but this is not exactly the way the building was performing. A few weeks before, we had the first round of smoke events. We found that we were getting, reductions that were up in here, whether the system was on or not. And we went in and did a little bit of poking around. I'm saying we, I mean, some others ended up doing that from facilities, and they found that some dampers were stuck that were not operating properly. I mean, gee, what a surprise, economizer dampers that don't work right. And there were also some filter problems where there was a couple of filters that had some bypass present. And so the fact that we had these low-cost sensors operating in the building allowed facilities to focus their efforts and attention on where buildings were not performing as well as we thought they should have. And so that was, I thought, a pretty decent success story. And facilities is actually pretty happy with this too. And we're working out ways to automate some of this, because this was, right here is not fully automated. I've had to download the data and process it. There's quite a few steps involved, but it is entirely possible to automate that. So we're sort of to wrap things up here, in summary, low-cost sensors, the PM sensors, they certainly can provide useful data. And I want to keep this emphasized, can. And we need to understand the data that we have so we can perform the proper comparisons. And part of this proper comparisons is, we really want to understand this indoor-outdoor ratio. And so just having a sensor that's inside your building, if things go up in the building, you don't know if it was a result of levels going up outside, or if it was a result of, somebody cooking in a kitchen that doesn't have a proper ventilation to outside. So you really need to be able to do that in pairs. And that doesn't mean that you have to have the same sort of sensor setting right outside of that particular building. Depending on where you're located, you may be able to have one sensor or two sensors for a campus of buildings, or if there's other publicly available data online, you can even use those. An example is the purple air map. If there's something within a kilometer or two away, and depending on your local terrain, as long as there's not a mountain between you and that particular sensor, or the bay coming in and the fog sweeping things around, causing microclimates, you can use that data instead. And the PM data PM particulate matter, not preventative maintenance data, can be used during these smoke periods to verify filter performance. And another one, which I didn't even touch on here, is several of these devices are also offering CO2 data streams. If we couple the CO2 data stream with verifying filter performance, then we can start to have a very powerful tool in our hands of, we've got smoke outside. We want to know it's in a yellow to red category outside, but if we shut down our outside air dampers to an extent and rely more on recirculation, are we getting better air quality, bringing it into closer to the green category? And what's our occupant density in the building? And are we getting adverse effects with the CO2? Because one thing that's important behind ASHRAE 62.1 is the 62 standards sort of rely on the fact that the air is generally better outside than inside. And if we have a smoke event, we know that's not the case, but we still want to pay attention to the CO2 numbers as we're reducing the ventilation rate. And I think that's all I've got prepared. So I will sort of open it up for questions.
Thank you, Woody. Again, I think you could hear the sound of applause from the audience if they were able to make their applause known. We appreciate the talk. I'm still waiting for some questions to come in, but I wonder if you could talk a little bit about competing. So we had Ian's talk about changing ventilation for COVID and some other ventilation issues, air change issues. When we have competing interests, we have wildfires, we have COVID, we have so many things. Are there differential ways to operate buildings, and do you have any recommendations in that regard?
Well, that's where I kind of left it with the CO2 side. I mean, just operating a building based on PM is going to be not the best idea. Because in a commercial building, in an office building, schools, things like that, the PM levels are generally quite small, and the PM is going to be coming from outside. Whenever we have an event where there are elevated PM, like with the wildfires, or if it's a school or some buildings, office buildings that are located close to freeways, we can have elevated PM. And there, a PM sensor is going to be useful. And some of the CO2 sensors are also getting quite good, where they are showing stable performance over a period of time. And the same $200, $300 device may include both PM and CO2. So you can start to get a good sense of what's going on and perhaps the trade-offs that are available. I mean, we just finished up a round of tests in Flex Lab at the end of the year, looking at as COVID-related ventilation work. And we're finding that the CO2 is a very good surrogate for the smaller particles, and understanding that your CO2 levels in the building and are how well mixed is the building will tell you something about COVID at the same time.
Interesting. Do you have any comments about ventilation within buildings where you maybe have to segregate a part of the building? You need to maybe in a home you've identified a need on one part of the building and a different need on the other part of the building. Yeah. Are there some things that people can do to meet different needs in different places?
Yeah, that's done a lot in, like at LBL, we have mixed use buildings. We have office buildings. We have buildings that have, are predominantly lab buildings. We have buildings that have a bit of both. And that the bit of both provides a bit of a challenge for the operators of the buildings, because you do have, like you said, competing needs. And then there's also fear that if we shut something down, is that going to change the pressure balances? And so if you have it, and hospitals are the classic example of that, where they want to have, negative pressure or positive pressure rooms, depending on what kind of patients inside those rooms. And I think sort of the general talk that I said here, you got to be careful whenever you're looking at those sorts of instances. You got to make sure that the system itself is still capable of meeting the design goals that they had as far as pressure boundaries are concerned.
Okay, thank
And
you.
I wouldn't worry about it too much in residential world. It's a lot different. I mean, in residential, if you've got, say, a sick family member with COVID, I don't know if Ian, hinted on this, but you got a large house, you stick them off and let them use their own bathroom, keep the bathroom exhaust fan on, don't mix too much between them, and you should be okay.
Thank you. We did have a question from someone about electrostatic filters. Is it possible to make some homemade electrostatic filters, and how effective are they?
I've never heard of anybody doing a homemade electrostatic filter. Electrostatic filters actually have very high performance. Now, there's a couple different varieties of electrostatic filters. I mean, there's charged media filters, where the filters themselves have an initial electrical charge, and they're generally made out of a polyester fabric, and it's the way they manufacture the fabric that it comes out with a static charge on it. And your classic electrostatic precipitator has a small wire that runs and has a discharge plate near it. There's maintenance involved with it, where you have to clean it periodically, but they are proven to provide high performance under this particle size. I wouldn't know about making one yourself.
Yeah, or calibrating it.
Yeah.
We have another question about Purple Air Network, noting that it's largely based on individuals with their own sensors. The question asks, would it be useful for commercial building operators to install their own systems, their own sensors for building management, especially in areas where wildfires are a consideration?
Yeah, the lab did just that. And so the Purple Air, whenever you get a Purple Air sensor and you go to, quote, deploy it, you have to make a decision whether you want it to be publicly visible, to anyone, or you can actually have it where it's just private to you. And Purple Air provides an API, so you don't have to go through their website to download the data. And so it is possible to work with, a Purple Air device on its own, where it's not visible to that public map, and use an API to retrieve data instead of going through their interface. And there are other companies that are providing, the same sorts of products that are more geared towards the commercial building world. I mean, Aware has a product that they call the Omni Aware, and it includes a decent PM sensor, as well as CO2 and a TVOC sensor, temperature, RH. And I think the one product that they have, it's everything's in a box that looks like a kind of like a thermostat, like a commercial building thermostat that mounts on a wall. And E-Likens is the company that we've been working with. It's developing something very similar. So there are options for the commercial building world, besides just Purple Air.
Okay. And do those also have a website, or do they also feed onto a website where you can get a calibration or get a sense of what else is happening?
There are people are doing different things there, and that's the one, my caveat I would warn people is to understand, are they leaning on the data in a way that's, you know, black boxish, or is it going to be obvious to the user? And so, I mean, that's my concern, is if it's a black box dynamic algorithm that's changing the numbers, you know, like every hour or so, then it's going to be hard to back up what you really have. And the general companies seem to be competing more on usability, UI, and perhaps I think they're even starting to think about providing some like reporting features to the consumer or to the client. I mean, and so what they may be pitching to the commercial building world may cost a little bit different than to the consumer world, because I think they're trying to use this sort of like a mindset of, well, we'll provide this reporting functionality, take care of the back end management, and not have anybody at the building worry about understanding an API and how to get the data out.
Okay. Um, we are almost ready to transition to the next round of talks, but you were getting a number of comments to appreciating your detailed attention to how to read this data and calibrate, and so I just wanted to make sure you had that information.
Yeah, and I'm available, so if people can reach out to me. You know, I'm pretty easy to find at the lab, and I left out all the details of how I got to the end point. So I thought it was more, you know, I can talk about that. We'll talk somebody's ear off about that if they are so inclined.
Thank you. Thank you very much. I wanted to mention to everyone here that we have an unusual situation in your favor, perhaps, and that is that the often when we have this institute, we tell you something about the internships at the lab, and then we say, oh, whoops, the deadline just passed. Well, that's not the case this year. The deadline is coming up, and I wanted to let you know that we have a booth in the larger space for this meeting. Our internship manager will be at that booth. She's already there now, and she will be there from now until 12:30. So if you have questions about internships at the lab, please go visit that space, and you can ask some questions there. Again, Woody, thank you so very much.